Welcome to this next lecture on acoustics. In the last class I said we will derive the Kirchhoff-Helmholtz integral equation for exterior problems. So now what is the exterior problem? The exterior problem is that I have a region with a volume V bounded by a surface S, and from here till infinity is my region of interest. Okay, I'm sorry, I have a so I have a region over here. I have a region over here which is outside a certain volume bounded by a certain surface S, and it goes off till infinity, and my volume of interest is here. This is my volume of interest. Okay. Now if I invoke Green's second identity again, and I say that I have now again a phi and a psi, two functions that have continuous second partial derivatives in a region bounded by now two surfaces. There is a surface at infinity and there is a surface at S, and in between is this volume V. Then I have this volume integral of phi del square psi minus psi del square phi over this volume is equal to this integral over these two surfaces, now S plus S infinity of phi del psi dot n minus psi del phi dot n over the surfaces. Okay. Now if we again connect to acoustics, okay, and say that I have sources for phi and psi, and let us say psi is the Green function, the free space Green function, let us put it that way, that is the free space Green function. Okay, that means is a solution to a spatial singularity delta function. Okay, but now sources for phi and psi are inside the region, inside the small volume. Inside this volume there are sources. So one set of sources, they generate here phi, and there is a point source which generates psi here. And I suppose I mentioned this surface S is imaginary, is an imaginary surface, it's not a hard surface in the interior case also, and we will do a problem later to demonstrate that S is an imaginary surface. Okay. So now if that is the situation, then phi and psi are indeed well behaved in this volume over here. This is the volume. Okay. So that again del square plus k square of phi is 0, and at the same k, del square plus k square psi is also 0, which means del square phi is equal to minus k square phi, and del square psi is equal to minus k square psi. So if I plug this back in here, if I plug this in here, what do I get? I have an integral over this volume, then phi del square psi is minus k square psi minus psi, and del square phi is minus k square phi, okay, over the volume. Now this is 0, is equal to 0, because these two cancel, this term and this term cancels 0. Okay, so as a result, now I have this combined thing of integration over this surface and the surface at infinity of phi del psi dot n minus psi del phi dot n ds equal to 0. Okay, so as before, this singularity, this delta function which is there within this smaller volume, I move it out so that now my singularity is over here. Okay, and so that now psi is no more well behaved. Why? Because psi has this form, psi r comma r dash as this form, e to the power of minus j k r minus r dash by 4 pi r minus r dash. Okay, and now because r dash happens to be, let's say there is this coordinate system. Okay, one is the integration coordinate r, the other is the location of the singularity which is r dash. Okay, so now because r dash is within the volume, r dash is within the volume, when r goes to r dash, psi blows up. So psi is not well behaved. Okay, and so we do the same thing here. We enclose this r dash with a small volume of epsilon radius, a sphere of epsilon radius. Okay, so that now I have integral phi r del del g del n r comma r dash minus g r comma r dash del phi del n for the first surface ds. Okay, here also n points away from the region of interest. Okay, so if I have this volume and the imaginary surface at infinity, S, and this sphere with epsilon radius, and this is the region of my interest. This is the region of my interest. Then the normal on this surface points inward, on this epsilon sphere points inward, on this infinity sphere points outward. Okay. So now this is the first term. Similarly, I will have a term that is on S epsilon phi r del g by del n r dash minus g r dash del phi r by del n on the surface ds. G of course has this form e to the power of minus j k r minus r dash by 4 pi r minus r dash at this form. So this is the second integral. Okay, let's call it 2, and then we have the other bounding surface, which is integral at s infinity phi r del g by del n r comma r dash minus g r comma r dash del phi by del n r. Okay, r must be denoted this way, and over ds r. Okay, because ds, the surface element, carries theta, phi and r at infinity. So in this case r shall go to the infinity. In this case epsilon goes to 0. Okay, so there are 3 terms, so we'll call this the third term. So 0 is equal to first term plus second term plus third term. Okay. Now this, in the interior case, for the epsilon surface, when it was inside and we were interested in the volume between the surface and epsilon sphere, the normal pointed inward. Now also the normal points inward. Okay, so there's no difference over there. Okay, so what will happen now is that we will have to deal with the third integral. Okay, and the third integral, I mean, we are taking r to infinity. That means we are taking values of these well behaved functions. Okay, and g to infinity. Okay, now if they are indeed sound fields or related to sound fields, they cannot have any finite value, at infinity. there would be something wrong if that was, even an atomic explosion here cannot render these sound fields infinite, have a finite value at infinity. So they will decay away. Okay, everything is bounded energy, they will decay away. And so right now I am just going to argue logically that integral 3 goes to 0, Okay. Later I will show using the Sommerfeld radiation condition, how that happens. So this will be a formal way to show that indeed number 3 integral goes to 0, but here even argumentatively it must go to 0. Okay. So these are physical values, these are sound fields generated by sources, they can't have finite values at infinity. So the integrand goes to 0. Okay. So the integral goes to 0. So number 3 goes to 0. So we are left with 1 and 2. We are left with 1 plus 2. Okay. So the 1 plus 2 will give back the same result, gives the same result. Okay. Except that now the normal has to be understood inward. So what is the result now? The result is this phi at r dash is equal to integral over this surface, the same surface, okay, which is g del phi by del n minus phi del g by del n. ds of r. Okay. So this is the same form as the interior. So this is exterior Kirchhoff Helmholtz integral equation. So the situation is the same. If phi is the pressure, if phi happens to be the pressure, then this is equal to particle velocity on this surface. Now we are looking at this surface. Okay. So if we know values of particle velocity and pressure on this surface, then we can go ahead and find pressure in the exterior region. We can find the pressure in the exterior region. Okay. So that's the exterior Kirchhoff-Helmholtz integral equation. So it has the same form, and we will use this in solving problems. Okay. Now there is something to be said about this issue that we have a singularity, we introduce a singularity at r dash, and we also have a sound field due to sources that cause the sound field phi. Okay. So what sort of an interaction is that? So we will discuss that a little bit. We will discuss that a little bit later. Okay. Now the next topic I want to discuss is this over here. We will be doing several problems in spherical coordinates. Spherical coordinates. Okay. So in order to do that, we need to understand the spherical coordinate and derive the general solution in spherical coordinates. Okay. So we'll look at that now. Okay. So let's see here. The wave equation, acoustic wave equation, in spherical coordinates is this 1 over r square del by del r square del p tilde by del r plus 1 over r square sin theta del theta sin theta del p del theta. Let me just keep the tilde out for now. Okay, plus 1 over r square sin square theta del 2p by del phi square is equal to 1 over c square del 2p by del t square. Okay, so let's give this a coordinate system. So this is my x, this is my y, this is my z. Okay, and we will measure theta. We will measure theta from the vertical. So this is theta. This is the polar angle. Okay. Then this will be the azimuthal angle phi. This is the phi angle, which is the azimuthal angle. So theta goes from 0 to pi and phi goes from 0 to twice pi. Okay. Now how do we solve this? So we use the method of separation of variables, okay, attributed to Euler. So Euler, who's supposed to have discovered, it's a great method. Okay, so what is this method of separation of variables? We assume that this pressure, which is dependent on r the location radius from the origin, on theta, on phi and on time, okay, to be functions which are solely functions of their arguments, r of r, theta of theta, phi of phi and t of t. Okay. And so if we substitute it into the PDE, what do we get? all the r derivatives apply to this function only, theta derivatives apply to only this function, phi derivatives apply to only this, and time derivatives only to this. So, we get 1 over r square. Now, this is a ordinary derivative, r square dr by dr, then we have theta phi and t plus 1 over r square sin theta d by d theta of sin theta d d theta of theta into r into phi into t plus 1 over r square sin square theta d 2 phi d phi square r theta t, on the right r theta phi by c square d2 t by dt square. Okay. So, now what we do, next step, we divide the entire equation by these functions r, theta, phi and t. Okay. So, if we do that, you can see that only 1 over r survives here, only 1 over theta survives here, 1 over phi survives here, 1 over t survives here. So what we will get is 1 over r square d by dr r square dr by dr plus 1 by theta r square sin theta d by d theta of sin theta d theta by d theta plus 1 over r square sin square theta 1 by phi d2 phi by d phi square is equal to 1 over c square t d2 t by dt square, and this okay. So, now let's just see what we have achieved. This is purely a function of r now. This of course has r over here. This is a function of r and theta, okay, and this is a function of r, theta and phi, okay, and this is purely a function of t, okay. So, such a situation is possible, okay, such a situation is possible only when this is equal to a constant. Here k is a real number, okay, and so it is positive, k square is positive, and we deliberately put this minus to make it a negative real number. It is a negative real number. Okay, and the reason is this. So, if we just take this time equation and this minus k square, Okay. So what do we have? We have 1 by c square t d2 t by dt square is, let's say, right now minus k square. Okay, minus k, but one case is let that be 0. Okay, I'm going to argue why minus k square has to be a negative real number. Okay, so one case we take is, suppose it is 0. Okay, so minus k square has to be a non-zero negative real number, but suppose it's 0. Okay, so what we'll get is that t double dot is 0. So that my t is going to be a plus bt. Okay, so that what happens now, as t tends to infinity, t starts to blow up. Okay, so this is not physically admissible. So the 0 value for k is not admissible. Okay, now similarly, suppose this is a positive number. Okay, that means what? 1 over c square t double dot is a positive number. It's a gamma square. Okay, that means what do I have? I have t double dot plus gamma square c square t equal to 0. Okay, and then what? How do I find the solution? I assume that t of t is some a e to the power st. Then double dot gives me s square a e to the power st plus gamma square c square. I'm sorry, this will be a minus here. Minus, a minus. Okay, this is plus over here, it comes in minus. So it comes here also with minus. Minus, okay. Then a e to the power st equal to 0. E to the power st is not equal to 0, a is not equal to 0. So I have s square is equal to gamma square c square, or s is equal to plus or minus gamma c. Okay, gamma is a positive real number, c is a positive real number. So that my solution now is that t of t is equal to a1 e to the power gamma c t plus a2 e to the power minus gamma c t. Okay, so now this term, as t tends to infinity, blows up. So that means gamma square being a positive number, positive real number, not allowed, or this right side cannot be a positive real number. So we will take minus k square, implying it's a negative real number on the right side. Okay, so now proceeding, what do we have now? Let's give these some numbers. We'll call this number 1. Okay, we'll call this number 1, call this number 2, call this number 3, this number 4. Okay, now we multiply the whole equation by r square. So we multiply by r square. Okay, so what that gives me is this. Okay, what that gives me so for the time being I will ignore this portion, number 4. I will take 2 and 3 to the other side. I will take 2 and 3 to the other side and bring minus k square to the left. Okay. So that gives me 1 over r d by dr r square dr by dr, okay, plus k square r square is equal to minus 1 by theta sin theta d over d theta sin theta d by d theta of theta minus 1 by sin square theta 1 by phi d2 phi by d phi square. Okay. Again we find this side is a function of r only and this side is a function of only theta and phi. And we will again choose a constant to proceed. Okay. So the time is up here. So I will close the lecture and continue from here in the next class. Thank you.